To this point, we've looked at kind of a history of the development of the idea of atoms, and we've also looked at 4 historical models of the atom. And now what we're going to do is look at some of the practical application for the course, where we're going to look at some different notations for tracking particles which are found in atoms. Before we do that, though, we're going to take one more stroll down a historical path, and we're going to look at a guy by the name of James Chadwick. So in 1932, James Chadwick provided a new interpretation of an experiment which allowed for the discovery of another particle in the nucleus, but this particle carrying no charge. Essentially, what this experiment did is it used magnetic and electric fields to deflect the path of a nuclei, and it found that they didn't bend quite as much as we expected them to. And that's because the nuclei were much heavier than expected based on their charge. And so there had to be some other particles inside the nucleus that didn't carry a charge. And those we named neutrons. Now it's interesting if you think about the timing of these things. In the late 1890s, you have the discovery of the electron. A little over 10 years later, Rutherford in the gold foil experiment discovers the nucleus and within them the protons. But then it's another 20 years before the neutrons are discovered. This is primarily because charged particles are really easy to detect because they respond to magnetic and electric fields. Neutral particles are much, much harder to detect, which is why it took a significant amount of time. And so now we have our kind of modern version of the atom, which is a nucleus containing protons and neutrons. It's at the center of the atom. And is incredibly dense, carries all the mass, and all of the space of the atom is taken up, mostly by empty space, but the electron cloud that then surrounds, that the electrons are moving around in, and those electron clouds, of course, are probability fields. And so any of these electrons can be at any place at any time, but the different electron clouds tells us the probability of where those electrons will be. And of course, as those energy levels get higher, the electron is more likely to be further away from the nucleus. Lower energy means closer to the nucleus. But that is kind of the very most basic explanation of the quantum mechanical model. And again, we'll have a whole chapter that will delve into this. Okay, so now into that practical application and looking at atomic symbols. So there are 2 types of atomic symbols you need to be aware of. What's called isotope notation, what's called element notation. Isotope notation is the notation for a single atom of a particular element. Isotope refers to a variation within elements where you have the same number of protons but different numbers of neutrons. And so when we're saying we're looking at isotope notation, we're looking at a particular atom of a particular element. When you look at element notation, you're looking like the boxes on the periodic table, and that is looking at an average of all of the isotopes of that element. And so the mass that's listed there on the bottom of that element notation is referred to as the atomic mass. It's measured in AMUs, which stands for atomic mass unit, and it's the average mass of all of the isotopes of that particular element. And so you have in the element notation typically an atomic mass. You have a number of protons, or what's called the atomic number, also sometimes referred to as the Z number. So for helium, that's 2. There are 2 protons in a helium. And then the element symbol. For the isotope notation, again, we use the same element symbol, but we have 2 numbers to describe which isotope we have. The bottom number is called the atomic number. The atomic number, again, is the number of protons. The atomic number identifies the atom. Everything that has 2 protons is helium, and every helium has 2 protons. If it doesn't have 2 protons, it's not helium. So that atomic number is the thing that defines what the atom is. And then we have the mass number. The mass number is essentially what's in the nucleus, because the nucleus carries the mass of the atom. So the mass of the atom is the protons plus neutrons. Again, the symbol for proton is P plus. That plus is a superscript. The symbol for neutron is N0. Notice we don't include the electrons in the mass of an atom. Electrons are significantly less in mass, and even large numbers of electrons don't significantly change the mass of an atom. It'd be like if you were driving your pickup down the street and it was loaded with bricks. and you drove onto a way station, you measured your pickup truck, and then you kept driving and a fly hit the windshield. Then you hit another way station and you weighed your pickup truck again, you're not going to expect a significantly different mass because a fly hit your windshield. Electrons are flies on the windshield of an atom. Okay, so those are the two notations you need to be aware of. So let's take a look at the breakdown. So here are a couple of elements. So let's start with the one on the top left there. So see if you can find that on the periodic table. Hopefully you sorted out that that was lithium. So we look at the two numbers, 3 and 7. The bottom number is the atomic number, which is the number of protons. So that lithium is going to have 3 protons. The 7 is how many protons and neutrons are in the nucleus. Well, if it's got 7 protons plus neutrons and 3 protons, how many neutrons is it going to have? Well, you subtract those two things and you're going to end up with 4 neutrons. This is a neutral atom, so there's no charge up on the top right. If it were not neutral, there would be a plus or a minus up there. So every neutral atom has the same number of positive particles as negative particles. So this lithium is going to have, or this lithium isotope is going to have 3 protons, 4 neutrons, 3 electrons. Let's go over in the top right and look at the He. So what is He? Well, we just looked at this on the last slide. He is helium. Helium is the second element on the periodic table. It has 2 protons. The mass of this particular isotope of helium has 4 protons and 4 neutrons. If 2 of those are 4 protons plus neutrons. If 2 of those are protons, that means the other 2 have to be neutrons. And because it's neutral, 2 protons, 2 neutrons, 2 electrons. Okay, take a look at the Kr. And so somewhere on your paper you might write that notation. Write down the name of that element, and then how many protons, neutrons, and electrons. You should pause the video and try that on your own. Okay, hopefully you paused the video. Come back. Kr is krypton. It's all the way on the right side of the periodic table. It's in a column that we refer to as the noble gases. We'll come back to why that is a little later in the year. The atomic number is 36, so that means it has 36 protons. The mass number, protons plus neutron, is 84. So you've got those things set up there just like a nice subtraction problem in your 4th grade math class. So you can go ahead and subtract the small number from the big number, and you should get number of neutrons at 48. And again, it's a neutral atom. And so there are the same number of electrons as there are protons. Okay, taking a look at this one again. Again, top number is the mass number. Mass number is protons plus neutrons. Bottom number is the atomic number, number of protons. So take a second. Look at those numbers. Again, pause the video. Protons, neutrons, and electrons, write them down. Okay, we got 50 protons. 119 protons plus neutrons, so subtract 50 and you get 69. It's a neutral atom, so we're going to get 50 electrons. Okay, on the right side of the screen, what I've done is given you the protons, neutrons, and electrons. Let's see if you can write the atomic symbol. Go ahead and pause the video and do that. Okay, so hopefully you found what element had 23 protons. So you're going to go on your periodic table and you're going to find the thing that has an atomic number of 23, and that's going to be vanadium. Element symbol for vanadium is a V. Element symbols are always capital letters for the first letter. If there's no second letter, then it's just the capital letter. So for instance, V. The one on the left we had SN. I didn't ask you what the name of that one is, but maybe you could look that up on your periodic table real quick. And you should see that that's tin, T-I-N. It's a metal. Maybe you're familiar with it. And notice the symbol is uppercase S, lowercase n. It's important that you maintain that system. If you had a capital in there, that would be a compound containing sulfur and nitrogen, which is different than capital S, lowercase n, which is tin metal. Okay, back over to the vanadium. We have a V there. Atomic number is 23, so the bottom you're going to write 23. Neutrons is 28, so 23 plus 28 gets us to 51 protons plus neutrons. And so we're going to have that atomic symbol there, and there's no charge because protons and electrons are equal. But here we go. What happens when we have this? Find the name of that element and see if you can take a guess, take a stab at what you think the protons, neutrons, and electrons should be. Go ahead and pause the video and do that. Okay, if we take a look at what's going on here, we have tantalum as an element. 73 protons, so the atomic number is always the atomic number. Whatever that number on the bottom is the number of protons. 180 protons plus neutrons, so you take 180 minus 73, should get 107. And then we have this 2 plus charge. It means there's 2 more positive things in this element than there are, or this particle than there are negative things. And so if you have 73 positive things, then in order to get a 2 plus charge, you're going to have 71 negative things. Now here's the thing about figuring charge. Once you fix the protons, figure out your charge by adding or removing electrons. Remember, electrons are on the outside of the atom. They're easy to take away or add to. Protons are in the center of the atom at the nucleus. They're pretty hard to get to and take away. In fact, it takes nuclear processes to break down a nucleus. And if you change it from 20 or 73 protons, then you no longer have tantalum. You'd have to pick a different element there. Okay, same thing on the right side. I've given you the protons, neutrons, and electrons this time, and given what we just did on the left, what can you figure out for that notation? Go ahead and pause the video and do it. So hopefully you identified which element had 34 protons, and that would be selenium, Se. The atomic number, the number goes on the bottom on the left side, is going to be 34. That's the number of protons. Protons plus neutrons, 34 plus 44 gets us to 78. That's the top number. And now does it have more positive charge or more negative charge? Hopefully you can look there and see there's more negative charge. By how many? And you should have sorted out there that it is 2 extra electrons. So now you're going to have a 2 minus charge. By the way, charges always go number and then sign. So when you're doing charges on ion, you do number and sign. If you do -2 or +2, you put the sign first. That's what's called an oxidation state, and that's a different concept. So science and chemistry in particular are about precise technical language. And so even the order of signs, the difference between uppercase and lowercase letters really, really matter. What we have here in these particles are not atoms. By definition, an atom is a neutral particle. So if it's not neutral, it's not an atom. And so these are what we refer to as ions. An ion is a particle that has an unequal number of protons and electrons. If there's more electrons, it's a negative ion. If there's more protons, it's a positive ion. Negative ions we call anions, unless you're Cajun, in which you call them anions. We don't actually call them anions. They're called anions. If you have positive ions, we call those cations. And you can always remember those because the T makes a plus, right? So cations positive, anions are negative. If you're Cajun, though, those positive ions are called cations. So what is an atom? There's a bunch of different definitions we can use for an atom. An atom is the smallest particle of an element that retains the properties of that element. So if you have a large sample of an element and you break it down in half and in half and in half and in half, you can keep breaking it down until you get to a single atom. If you break that atom apart, you're now not going to have that element anymore. It's almost also, and this is one of the things that Dalton said to us, it's the smallest particle that matter can be separated into by chemical reactions, right? So chemical reactions can only rearrange atoms, and one of the ways we can rearrange them is to break all of the bonds, and so you have just elements. So they're not the smallest particle completely, but they are the smallest particle in chemistry. They're the smallest particle that you can break things down into chemically. And by definition, an atom is electrically neutral. If you say atom, that means protons and electrons are equal. So you will often hear people refer to ions as charged atoms, and I will every once in a while even slip and say that, but that's technically an oxymoron. To say a charged atom, right, is to say that you have something that's by definition neutral, is charged. So really, a charged particle is referred to as an ion. A neutral particle is referred to, or at least a neutral particle with a nucleus and electrons is called an atom. So there's a table you should be aware of, and you should go ahead and jot this stuff down. And these are particular pieces of information about these three subatomic particles, which are kind of a central feature of the building blocks of chemistry. So we have protons, we have neutrons, we have electrons. The symbol for each of those, P plus, N minus, E negative. Again, those are superscripted symbols next to the letters. The charges, again, most of you knew this before you walked into this class. Protons are positive, neutrons are neutral, electrons are negative. And relative mass. We talked briefly about AMUs. And AMU, we're going to talk about that more in more detail in some later chapters. But the short version is it's a system of relative mass whereby a proton weighs 1 AMU. A neutron also weighs about 1 AMU. Now, these are not exactly the same mass. And again, we'll talk about why that is a little bit later. And then electrons, we already talked about, significantly smaller than protons or neutrons. They are 1 over 1840, almost 2,000 times smaller than a proton or an electron, which is why their mass, even if you have a lot of them, has very little impact. We don't have any elements that are going to have 2,000 electrons in them, or even 1,840, which is what it would take to equal 1 AMU. And again, atoms, as we talked about back with Dalton, one of the things Dalton was right about, atoms are submicroscopic. No one has ever seen an atom. No one ever will see an atom. One of the ways we do know, though, that things on the atomic scale exist is we have a thing called a scanning tunneling microscope. The picture on the left is a picture of some of the inner workings of the scanning tunneling microscope. You are not to make any sense of that. I'm not sure that I could. On the right, we have the type of image that a scanning tunneling microscope measures or produces. And this is a picture of a scanning tunneling microscope image, words are hard, of graphite, which is what's in your mechanical pencils, right? And again, this is not a lens image of this. So this is not looking through a standard optical microscope. So what you have in a scanning tunneling microscope is a tiny charged needle that deflects around electron clouds and measures where those electron clouds are. And so what you're seeing here is a computer-generated image of where a needle set electron clouds were in a sample of graphite. And so this is filtered through a computer that has to build this image from the data from the machine. So that's when we say we look at atoms with a scanning tunneling microscope, it's being filtered through a computer program. So that is kind of, in a nutshell, how we sort out atomic symbols in this video. And there's going to be a handful of applications of that as we move forward.